So now let's talk about a new method which lets you to compare average of more than two populations. Actually, you can also use it for two populations. Instead, in this case, the ANOVA results will be identical to t-test. Okay, so the method, as I already mentioned, is called ANOVA, and the main idea is that ANOVA helps you to compare means of several populations in case if you have more than two groups, and also in case if you have several factors. First, I will talk about one-way ANOVA. It's when you have only one factor, and then later we will also discuss n-way ANOVA. But this topic, one-way ANOVA, will also be split into at least two videos. Okay, so let me show you the intuition first. So again, like in the previous video, we work with three samples that came from three different populations, and then we assume that populations are normally distributed, and the variances or standard deviations of the populations are identical, are the same. Okay. Then in this case, we can define that, okay, every time we take a sample from any population, this sample is normally distributed, we have the expected value, and then we have this random part, the variability of this value, right? And then we can write it for every sample. No? This is our null hypothesis, that the population have the same means, so there is no effect regardless which of the, for example, popcorn brand you use. Okay. I forgot to mention that in this case, I will use another example. It's not about popcorn. In this case, I run chemical reaction with three different catalyst types. So this is catalyst A, this is catalyst B, and this is catalyst C. And the outcome, the response in this case, it's a yield. It's how many grams of a final product I get after you run this reaction with particular catalyst. So you can see that I have approximately 39 grams, a little bit less, a little bit more in the case of catalyst A, a bit over 40 when I use catalyst B, and again around 39 when I use catalyst C. So my goal is to find out which catalyst is best, or actually if catalyst has any effect on the yield. So maybe all these catalysts are the same. Okay. So now let's think, if we indeed assume that the populations are normally distributed, we can write this in a matrix form, right? So these are all x values we got from the first population. This is all x values we got from the second population. This is from the third population. And when I say x values, I mean the response in this case, right? So it means that, so all these values, for example, this one, you remember, this is how we define it. It came from population with this expected value, and this is the random part. That's exactly what I write here. Look, this is the expected value, and this is the random part, right? Now, this value came from the same population, so the expected value will be the same, but random part will be different, right? This value came from population with this expected value, and this is the random part, right? So I simply wrote these expressions for all values in my particular case, right, in my particular sample. Now, on the other hand, if you think about all these z-scores, well, z-scores are standardized, normally distributed values. They do not depend on the population, right? So they are all the same. It's like they came from the same population. So therefore, I can remove the color coding from the z-scores, right? It's just random numbers. So it's just random numbers. So this part does not depend on which population the values come from. Also because, you remember, we have the same sigma. So it means that we will see the difference only in this part. So only expected values are different for the populations. Moreover, because we have sigma in every part of this table, of this matrix, I can just move it outside, right? So these are just standardized values normally distributed. This is sigma, common sigma, and these are the average values, right? Now I can compute a variance for every part, for every matrix here. So if I compute variance for the values, that's what I call a total variance, because it's a variance of my original data set, right? But I can also compute the variance of means, right? And in this case, I call it systematic variance, because this is the variance between the groups. This is the effect I'm looking for, right? While this variance will be totally random, because we know that z-scores are random numbers from normally distributed population, so that's what we call residuals. This is what is rest when we remove systematic effect from the data, right? So this is the variance of the mean values, and this is the variance of this part of the residuals, right? Why variance? because that's exactly what I want to replace the difference with. Remember, difference, you can define difference between two values. But if you have more than two values, how to define difference? It's very difficult to define difference, but difference is a distance. How we compute distance if you have more than two values? We compute variance, right? You remember that if you have three values, you compute mean, and then you compute distance between the mean and every of these three values. Then you square these distances, you square these distances, and then you compute sum of squared distances and average it. That's exactly what variance is. So variance shows you this spread, the variability of the values, and it's exactly the substitute of the difference, although it's squared difference, right, for the case if you have more than two. So that's the main trick. We use variance instead of difference when we estimate effects, when we estimate variability. Okay. The rest is the same. You remember in student's t-test, we took difference of means and divide to the variation of the noise, right? The same idea here. So instead of difference, we will take variance of means and divide to the variation of the noise. So that's the intuition. Now let me show you how it works. So first of all, this is our null hypothesis, no effect. If null hypothesis is true, then this will be zero, right? If all mu values are equal, then the variance of these values will be zero, of course. But noise is never zero. So it means that if you take effect to noise ratio, you will have zero. That's our expected signal to noise ratio. It's similar to t-score. You remember the t-score, if the difference of means in the two sample t-test is zero, then the t-score is also zero. It's our expected value, right? So that was the theory. That's the expectations. Now let's talk about the reality. In reality, we don't have the mu, but we can compute the average value for every sample. We can compute average of the sample, and therefore we substitute mu with these average values, right? So we say this is average of your sample plus residuals. This is average of our sample plus residuals and so on. So you can now see what is residuals, right? Residual, we also define it in the t-test. It's the value minus the mean of this particular sample the value comes from, right? So again, like in the theoretical intuition, we can call this one as a systematic variance. If we compute variance of these mean values, we can call it systematic variance, and that's what we define observed effect. So instead of m2 minus 1, m1, so that's the observed effect in case of two samples, we compute a variance of three mean values, and that's the observed effect in this case, in the case of ANOVA, right? So now we define the observed effect. Then the variance of the residuals, it's the noise. It's the noise. It's the analog of standard error squared, right? And now let's think, if expected variance, the variance of population means is zero, and it will be zero if null hypothesis is true, right? But the calculated, the observed effect is never zero. The variance of mean values will never be zero, because you remember mean values are also random values. So it means that the variance of mean values also be a random number. But if it's random number, most likely, not always, but most likely, it follows certain distribution. And then we can see how far this random number can go from zero if null hypothesis is true. So you can see that, again, we have a very similar situation to t-test. So we have a score, which is a ratio of these two variances, the signal to noise ratio. And then this score is a random number. We have the expected value for this score. If null hypothesis is true, it's zero. And then we can use distribution to see how extreme the observed value is, how far the observed value is from the expected, and how likely you can indeed observe this value if null hypothesis is true. Okay. Now let me show you the calculations. Let me show a particular example. I simply took all these numbers. You can see these values are here, these values are here, and these values are here, right? Now I compute average. You can check me if you want. You can compute average of all these four values. You will get 37.1. Average of these values will be 42 and 38.8 for green ones. Now I can split my original values into sum of two terms, right? First of all, it's the systematic part, right? You remember I simply put the averages here. Averages here, right? And then residuals, I also need to compute residuals, so these are residuals. Let's check how I got this one. You remember residual, its original value minus its average. 38.5 minus 37.1, it's indeed 1.4. For example, 36.4 minus 37.1, you can see this is smaller than this one, so it will be negative 0.7. Okay, so these are residuals. This is what happens with my values if I remove the systematic part. Okay, now I compute the variance of these. It will be my observed effect. And how to compute variance, we know we need to subtract the global average from all these values and then take a sum of squared distances between every value here and the global average, right? And then divide it to degrees of freedom. And then I can also compute the variance here. And here it's easy because the average will be 0, so I just need to compute a sum of squared residuals, right? But now look, because I need to subtract 39.3 from every of this value, I can do it in advance. So I can write it like this. So I had 39.3, and then you can see this is minus 2.2. How this I got minus 2.2? It's exactly, if you take 39.3 minus 2.2, what will you get? You will get 37.1, right? If you take 39.3 minus 2.7, you will get plus 2.7, you will get 42. And then if you get 39.3 minus 0.5, you will get 38.8. I just put this global big average in front of it. So now you can see what is called ANOVA model. It tells you that your values, it's a sum of three components. The first, it's a bias. It's just a global average of all your values. 39.3, it's global average also of all your values. Then effect, it's a systematic part. It's a systematic variation which is caused by presence of several groups. And residuals, which is a random part. Right? And the overall idea is to estimate variance of systematic part, estimate variance of residuals, and take a ratio of these two variances. That's what we are going to do, right? So let's calculate the variance. You remember, because we already have like m1 minus m, right? So all these values, it's already where we subtract the m. To compute variance, we simply need to take a sum of these squared values because we already have distances. So you take minus 2.2 squared plus 2.7 squared plus minus 0.5 squared and then 4 times, right? That's exactly 49.5. Again, check me. You can use Excel or R to check that this is correct. Likewise, we compute sum of squared values here. So this is the sum of squared values, sum of squared distances between the values and the mean, right? Now degrees of freedom. This is a little bit more complicated, right? So remember that at the beginning you had 12 degrees of freedom. Then you use 1 degree of freedom here because you computed average, right? And then here you have 2 degrees of freedom because you remember you lost 1 degree of freedom. So these are distances between average values of every sample and the global average. And you have 2 independent distances, not 3, right? You can also see it clearly because they sum up to 0. So it means that if you don't know, for example, this one, if this one is hidden, you can easily calculate this one by just taking the difference, right? So 0 minus 0.5 minus 2.7 will be minus 2.2, right? So you have 2 independent distances here. Then how many you have here? Well, apparently you had 12 at the beginning, and then you lost 1 here, you lost 2 here. You remember to calculate the residuals, you need to take a value minus this, and then minus, for example, this, and this will give you the residual. So it means you have 12 minus 1 minus 2, you have 9 degrees of freedom. And that's what I have here. So here we have 2 degrees of freedom, here we have 9 degrees of freedom. Now we know how to compute variance, because variance is a sum of squared distances divided to degrees of freedom. So this is the variance. I use MS, it means mean squares. It's another, just a synonym for variance. So this is the variance, this is my observed effect for the systematic part. This is the variance of the random part. Okay. So you can see that this one is much larger than this. Much larger. So let's calculate how much the ratio between the systematic variance and the random variance is called F value or F score, similar to T score. So it's simply a ratio between systematic part and the random part. It's a signal to noise ratio. I can compute it just by taking this divided to this, and then you can see it's 8.41. If null hypothesis is true, then the expected F value is 0, because in populations you have no difference between the average values, and that gives you the variance of 0. So we expect F value equal to 0, but we got 8.41. Is it possible to get 8.41 or larger if null hypothesis is true. That's exactly what we need to investigate, right? So like right now we know that our systematic variance is 8.4 times larger than the noise variance. And that's kind of a big number, right? We know that the signal is much stronger. The variance between the groups is much larger than the noise variance, than the residual variance. But everything is possible in this world, so we need to assess this probability first. Okay. So F values follow a specific distribution. It's called F distribution. F stands for Fisher. It was a famous statistician, so we will call it F distribution or Fisher distribution. The F distribution has two parameters. It's the degrees of freedom for systematic part and degrees of freedom for the random part. What you see here, it's F distribution for 2 and 9 degrees of freedom, exactly our case, right? And then you can see that anything between 0 and 5, let's say 4 maybe, right, will not be very extreme. But our F value is 8.41, it's here. So what's the chance to get F value 8.41 or larger if we assume that if we expected F value is 0? Well, you need to compute this area, which is barely you can see, because you can see that the curve, the density distribution curve almost touches 0, but I can compute it using R, for example, right? So you can say P function for F distribution. This is the F value. This is the degrees of freedom for systematic part. This is degrees of freedom for random part. And because it's a right tail, I need subtract it from 1. So that's my P value. That's the area. So you can see it's 0.009 approximately. So 9 in 9 out of 1,000 cases, if null hypothesis is true, you will see F value as big as this one or bigger. Okay. So that's my P value, 0.087, which is quite small. And of course, it depends if you need to make a decision, it depends on the significance level. But in most of the cases in this particular situation, you will reject null hypothesis and assume that continue as if you have an effect indeed. Okay. Now let me show you how to do it in R. First of all, you need to enter this data. And in this case, you need to enter both the yield, the response values, and the groups. So this is how to do it. You can see that I simply enter it every sample separately. I saved values for every sample into separate variable. And then I combine them into one single X variable. So X is this column here. Okay. Then I also entered the groups. This is how I do it. Instead of entering A, B, 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 C, 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 I simply say repeat A 4 times, repeat B 4 times, repeat C 4 times, right? And then combine them together. And then it's very important that the grouping factor, the factor, any factor in ANOVA, should be turned to factor. So you remember we discussed factors at the very beginning. So factor, it's a categorical variable in R. So you need to tell R, it's a categorical variable, it's not some numbers or characters. And after that, the rest is easy. You simply run ANOVA like this. AOV, it's analysis of variance, it's another acronym for ANOVA. This is the response. This is the factor, right? And you remember little tilde means relation mark, right? So we say X depends on G. So how the yield of reaction depends on the catalyst type. And then I write summary M, and I got the table. I cut it a little bit to make it short. And then if you look at this table, you will see a lot of numbers. But if you compare these numbers with these numbers, you will see most of them are almost identical. For example, this one is degrees of freedom, 2 for systematic part, 9 for residuals. We have 2 for systematic part, 9 for residuals. This is sum of squared distances, 49.62. We got 49.5 because I rounded the values in my calculation, so it's a little bit different, but very close, you can see. This is 26.5, and we also got 26.5. Mean squares variance, 24.8 here, we got 24.8 if we round it to one decimal. 2.95, 2.94, 2.94. This is the F value, again, very similar to the one that we have, a little bit larger. And this is the P value, which is also quite similar. So this is how to do it in R. And then you can see that our manual calculations, they match the calculations in R very closely. Okay. So this is it. Now you know how to use ANOVA to estimate if the observed effect, how likely the observed effect is just by chance, right? So remember, the null hypothesis is that all means are equal, and it doesn't matter how many means you have, 3 or 30, of course 30 probably too much, but 3 or 5 or 7, it's always the same. The observed effect you compute by taking average of every sample of every group and then computing variance of these average values. And you can also standardize this variance by dividing to variance of your residuals, of your noise, and that's what we call f-value. So f-value shows you how much time your variance of your mean values is larger than the variance of the noise. And you can see in our case, it's 8.4 times larger. So it's a very strong signal. It's a very strong effect compared to noise. Then you can compute a p-value, and p-value shows you a chance to get f-value as big as you have or bigger if null hypothesis is true. And then if these are the degrees of freedom. So it means you have 3 groups, that gives you these 2 degrees of freedom. And then you have 12 values in total, that gives you 9 degrees of freedom for the random part, right? So conclusion in this particular case will be that it's very unlikely that the observed difference or observed effect is due to a random chance. So it means that we should proceed, we should make a decision if indeed one catalyst is better than the others. We still don't know which one is the best, but we know that there is an effect. We know that catalysts are not equal. And that's already a very important achievement. In the next video, I'll show you another example for ANOVA, similar to this one, but just a little bit different data set and so on. Another example.